for chemical properties, let's begin with the stereochemistry. Tetracyclines, they have some carbons which can be chiral. For example, for doxycycline and oxytetracycline, these two, they have OH group at position 5. They have OH group at position 5. So they have 6 chiral carbons. They can have 6. Then for other tetracyclines, they have less than 6 chiral carbons because they have no OH group at position 5. So others have less than 6 chiral carbons. Now, for pKa, tetracyclines, they have 3 pKa. We have pKa here. This pKa is acidic, so it's around 3.1 to 3.4 for tetracyclines. Then we have here for this amino group, it has a pKa of 7.1 to 7.9 pKa. So this one is from 2.8 to 3.4, which is acidic. So this one is from 9.1 to 9.7. It is basic. Then when it comes to this one, here we have a pKa, which is slightly neutral from 7.1 to 7.5. So those are the pKa's we have for tetracyclines. There are 3. We have the basic pKa, then acidic and neutral groups. Then for chelation, these tetracyclines, they have a tendency to chelate the polyvalent cations. These ones can be calcium, can be aluminium, you can have magnesium, so, and many polyvalent, so more than one valence. So tetracyclines, for example, this is ring A, this is B, C, and D, like this one. Now we have a OH group here, so to exist as a O, then here we have this. So this one will be inverted now. So this one will be the O. This one will be the, so to be like that. Now the cation, for example, can be represented by M. So this one will form a bond with the cation, and this one will form a bond. So this one is represented as arrow. It's a dative bond. So they are represented as arrows because oxygen should have 2 bonds, of course. Now these ones, they are represented as single bonds. Then these ones are represented as arrows, those 2. Or sometimes, instead of using this, you can just draw the O, even this one, the O. So this bond can move, right? So you have your metal cation. So they form a bond. So they form bonds. So this one will be minus, of course, this one will be the cation. For example, in case of magnesium, so it's 2+. Then this bond rotates from between these 2 oxygen atoms. So you can represent it as this one or like that. So that's chelation. Then for these chelated metals, we form the insoluble complexes which are not easily absorbed. So they remain in the GIT in case of oral, if it's oral. Then for we have finished chelation. Now for epimerization, these tetracyclines at pH of around 2 to 6, they tend to undergo epimerization. This is the ring A, this ring. So this one, here we have mineralization or tautomerization. This bond will pull electrons. So when it pulls the electrons, this carbon will be unstable. So this bond will move to stabilize this atom, to stabilize this carbon, and stabilize this one. But this one will be unstable. So we can have a bond from this oxygen, but sometimes this hydrogen is lost. So it will be lost to form a bond here. So at the end, you have your ring looks like this. Here you have formed a bond, but you have lost the hydrogen or the proton. So you have your dimethylamine, and here there is OH group. Here you have formed a bond. This one is O minus. So you have this one. But again, this bond can reform back. Then this one will move back, and this one will get the proton. To get the proton. So when it gets the proton, it can go back to this group and form a ring like this one. So this is the alpha orientation. So this nitrogen, it's the dashed bond, and this one, the hydrogen is on the wedge bond. But sometimes, if it comes back, if you get the proton, it may not look like this. You shall get this. So instead of hydrogen going back to the wedge bond, now it will shift to the dashed bond. So this wedge bond now have the dimethylamine on this bond. Then this one will form back like this. Then you have your O down here. There's O. This one remains the same, but you have changed the orientation. So this orientation which has changed, now this one is called the tetracycline. So, and this substance now, the product is inactive. So the tetracycline will be inactivated. So it is inactive tetracycline at a pH of 2 to 6. Then, because of the change in orientation, so binding will be difficult. Because if the binding site likes this orientation, this one can fit, but this one won't fit because of the change in the configuration. Now, for dehydration, this one at a pH of less than 2, acidic pH in the stomach, tetracyclines are inactivated, so they are acid labile. So if they are taken orally, especially those tetracyclines with the OH group at position 6, this is position 6, and you have a methyl group, meaning that this is the tertiary alcohol. This one is tertiary. So all those tetracyclines with a tertiary alcohol at position 6, they undergo this mechanism, as we are going to see, and they are inactivated. So those ones which lack this OH group, they are safe. They are not liable to this acidity. So what happens in presence of an acid? This O will attack the acid. So when it gets the acid, it will become plus. Let's see. So it will be plus. So we shall have, okay, let me draw it here. So we have this OH. Now this O is now O with 2 hydrogens, so it is plus. It is plus. Remember, this is the saturated carbon, meaning here there is a hydrogen atom. So this one, the oxygen, since it is unstable to breaks off. When it breaks off, this hydrogen will saturate, will stabilize this carbon, because this carbon will become plus, then this hydrogen is lost to stabilize this carbon here. So we shall have a double bond here formed. So when you have a double bond formed, this one is lost. So we shall have minus water. And this hydrogen is lost, so we get the double bond with a methyl group remaining and a double bond here. So here we have the O and OH here. Now, this O will pull the electrons. This bond will, now oxygen will pull the electrons. When it pulls the electrons, this one will become plus, the carbon will become plus. So when it becomes plus, this bond will move and saturate this carbon. So meaning that this one will be also unstable. So this oxygen will form a bond back. When it forms a bond here, it saturates this carbon, and so this hydrogen of course will be lost. So you can draw it like this. So just draw a bond from hydrogen directly, form a bond here. So this hydrogen is lost. So we shall have this ring saturated now. So when this oxygen pulls the electrons, it can gain the hydrogen from here. So we shall have this oxygen. Now it is OH, and here it is OH. Now this ring is saturated because we have formed a bond here and here. So these two rings, so this is the naphthalene ring, the naphthalene. Naphthalene ring is formed because these two carbons, these two rings are saturated, and methyl group will remain. Other groups also, they will remain. So this group or this product is called, so it's at position 5A and 6. So it will be 5A, 6, and hydro tetracycline. So it is 5A, 6, and hydro tetracycline, because here we have lost hydrogen, so we have formed a bond here. Now, if it happens that this process and this one, they happen on the same drug, this is ring C, this is ring C, this is D, and this is ring A. So if ring A undergoes the epimerization, and also ring C undergoes the desaturation, right? So we shall form epi and hydrotetracycline. This is epi tetracycline, this is anhydro tetracycline. So the product will be epi and hydro tetracycline. So this one combines both of them, and this product is nephrotoxic. So this product is nephrotoxic. It leads to Fanconi-like syndrome. Fanconi-like syndrome. So this term is used to mean the inability of the kidney to reabsorb some of the substrates from the urine. So this is what epi anhydrous tetracycline. Now, when it comes to lactonation occurs at acidic pH, basic pH, or pH greater than 8.5. So, tetracyclines are complicated. They are inactivated by acid and also by the base or alkalinity. So, this one, in presence of a base, so in the intestines, so we shall have this process happening. This OH will be taken. So this one will be O minus. If this one is taken, these electrons will be given to oxygen. So if it is O minus, meaning to be like that. So when it's O minus, now this one will form a bond. When it forms a bond here, this one will have excess bonds. So this bond will attack the hydrogen from the oxygen up. So we shall have O minus now when this hydrogen is taken, because these electrons are given to oxygen. So we shall have O minus. So at the end, we shall have this bond is not there, and here we have formed O and a double bond. This one, this bond has taken the hydrogen, so mean that this carbon will be saturated, will take the hydrogen. And this oxygen here will have excess electrons. So remember we have, this one will pull electrons, this oxygen. When it pulls the electrons, this carbon will be plus, will be unsaturated. Will be unstable. So when it's unstable, this oxygen will now attack this carbon. So we shall have this bond. So this oxygen, here there is a methyl group, and this oxygen has formed a bond here. It has formed a bond here. It has attacked this carbon. So this is O minus. That's what we have. Now, this oxygen will form a bond back because it is unstable. When it forms a bond back, this bond will break. This bond will break. So when it breaks, it will take the hydrogen. So we shall have this oxygen going back, so it will be O, and this ring will remain like this. So everything, other groups will remain, but the change will have, the change will be on the ring C. So this is the lactone ring. So we form the lactone ring. Oh, this one is called isotetracycline lactone. It is isotetracycline lactone, and it's also inactive. So we have seen the stereochemistry. We talked about the pKa. There are three. Chelation, we have seen chelation. Epimerization, we have seen it at pH of 2 to 6. Dehydration at pH less than 2. Then lactonation occurs at basic pH. So in basic pH, we shall form this one, the lactone. Then in acidic pH, we shall form the anhydrous tetracycline. At this pH 2 to 6, we shall form the epitetracycline. This epitetracycline is nephrotoxic. It leads to Fanconi-like syndrome. Yes, guys. Now let's talk about the mechanism of action.